Jó estét kívánok! Thank you guys for coming. So today we have as our guest here in Budapest and for MCC and specifically for the Climate Policy Institute, we have Professor Stephen E Koonin, and it's a great honor to have you here, flown in from New York yesterday. So Professor Koonin is a former professor of Caltech for 30 years and a theoretical physicist by training and an expert in computational modeling. And he's currently professor at NYU. He has a wide range of experience. He was the chief scientist at BP from 2004 until 2009. And then for 2 or 3 years, from 2009 to 2011, he was undersecretary for science at the Department of Energy in the first Obama administration. He's the author of this book we have with us today in the Hungarian edition, which came out last year. But its original was in English, published 2021, and the title in English was Unsettled, or is Unsettled, What Climate Science Tells Us, What It Doesn't, and Why It Matters. So we're really, really grateful for you being here today. And I think originally we had a plan, you're going to do a presentation, but we were talking earlier, and I think we had quite a good discussion, so we thought maybe we'd just have a discussion. And the first point would be, well, first of all, tell us what the book's about, and just in general, and then we'll get into your motivation and so on.
So, first of all, pleasure to be here and talking about subjects that are important to everybody in the world. The book is really 2 parts. One is a discussion of climate science, what we know and what we don't know about the changing climate, how it might change under human influences going forward, and what the impacts might be. The second part of the book is really about how should we think about responding to that circumstance, what might work, what might not work, and so on. And I think what's distinctive about the book, good academic that I am, I took everything in the book from the UN climate reports, or the IEA energy reports. So in some ways the content of the book is not mine, but it is what the science and the technology really says.
Well, the title obviously is provocative. It's Unsettled. So in summary, what is unsettled with the climate science?
Yeah, so I like to think about the title as really a triple entendre. First of all, it refers to the state of the science itself. There are important things about the climate that remain to be understood with enough precision to be confident in how it might change in the future. It also refers to how I felt when I first learned about those uncertainties. I'm a physicist. I had not looked deeply into climate science until about 2014, roughly 10 years ago. And when I did, and I found out how unsettled it was, I became unsettled. And then finally, the unsettled refers to, well, what are we going to do about all of this, which is playing out in society, in the newspapers, almost as we speak.
Well, before we get on to the question of what is unsettled about what we do, I mean, why were you unsettled by it? What was so unsettling?
Well, starting in 2004, I joined BP, and I came aboard to actually figure out what beyond petroleum really meant. And so I was focused on energy technologies, alternatives and renewables, what would work, projected costs, things of that sort, and had not looked deeply at the science of climate. And that happened in about 2014, and as I said, I was somewhat shocked at what I found out.
Why were you shocked?
Because I had heard, certainly the mantra in BP and what you heard in the media and from the politicians was the science is settled. We've got to go ahead and make dramatic reductions in our emissions, otherwise the planet is doomed. Well, you can fill in the rest. I'm sure you've heard much the same things, even up until today.
Something I find quite interesting about the concept of there being a consensus or the science is settled is that I'm not a scientist by training, I'm a social scientist, and they're not the same thing. But I find that my understanding of science is that friction is a dependable source of illumination, that science is precisely will say that nothing is really settled. I mean, in physics you have quantum mechanics and relativity. They both seem to work. They're not reconcilable. So clearly something isn't settled. So why is it this topic draws the rhetoric of something being settled?
I think, first of all, everybody's interested in it. The fate of our planet, allegedly, is really important to everybody. The second is it implies there are limits to human carrying capacity of the planet, and that goes against some people's moral sense. And I think the third is that energy touches everything. And if you're going to change the energy system, you are going to disrupt a lot of things. And people feel very deeply about all of that, which is why I think the politicians in the media, and unfortunately some of the scientists, have adopted the mantra that it's settled and we got to do decarbonization, otherwise we're all going to burn.
Before we were discussing a whole range of issues around the science of climate change, but first it's worth talking about the science itself. So as a scientist, reading the literature on climate change, looking at the UN's, the first working group on the science, what was in fact so unsettling for you? Can you give some examples?
Yes, so let me refer to the most recent report, which is AR6 that came out about a year and a half ago, Working Group 1. And for example, there are no long-term trends in most severe weather phenomena. That includes tropical cyclones, hurricanes, floods, droughts. There's a wonderful chart in chapter 12, I think, of that report that lists about 20-something different long-term trends, and maybe 5 of them show some identified trend, and the rest of them show nothing. We can go into the impacts of severe weather, what's been observed, and so on in a bit. A second is that there is a broad uncertainty in how the temperature of the planet is going to respond to growing greenhouse gases. And there are technical reasons why it is uncertain we could go into if you want. And maybe the third, which is kind of astonishing to me, is that the projected economic impact, whether it's for the US or for the globe as a whole, of a temperature rise of, let's say, 3 degrees, is a few percent. Namely, the economy would be a few percent smaller when the temperature got to 3 degrees than it would have been otherwise.
So
That's in the noise.
The economy would grow, you're saying?
The economy would still keep growing. It would just be 3% smaller in, let's say, 2100 than it would have been otherwise. And that, as we physicists say, is within the noise.
I mean, do you think the problem with how people look at climate change is the science as such, or is it the significance and the status we give the science?
I think the science is problematic, okay, for several reasons. One is that we have a poor historical record. We only have 150 years, really, of temperature measurements around the globe. The longest record goes back to the late 17th century for one small region of central England. The second is that most climate happens in the oceans. The oceans are the long-term memory of the system. Remember, climate's a 30-year average. And we have very poor knowledge of the ocean at depth. And then the third reason is that human influences are a 1% effect. The average sunlight and heat coming in and out of the planet is about, I'll use the numbers for a minute, 240 watts per square meter. The human influence on that, due to greenhouse gases and aerosols, is about 2.5 watts per square meter. So we're trying to find a 1% effect on a complicated, noisy system for which we have incomplete data. That's a wonderful scientific challenge, but it also means it's really tough to make supportable statements that can inform public policy.
Well, this is an interesting question about public policy, and when we were talking earlier, we both mentioned the COVID comparison. And I wonder if you could talk about your perspective on the parallels you see between the way people talk about COVID and climate.
Yeah, so there are a group of scientists who are an expert in the science at issue. In the case of COVID, it was the virologists and the epidemiologists, and of course the docs, the MDs. In the case of climate science, it's the oceanographers, atmospheric physicists, ecologists, and so on. And in the COVID case, you had the doctors single-minded, the experts single-mindedly focused on saving lives, or more precisely preventing people from getting infected. What we found out in COVID was that that was not the only consideration, because the measures that were taken to achieve that goal also had their own damaging impacts. The lockdowns, for example, delayed the educational progress of a whole several-year cohort of young kids and crashed the economy and so on. So you had to balance during COVID, and we, at least in the US, didn't do a great job of that, balance the epidemiological issues against the societal impacts of the responses. Climate science is the same way. Climate scientists saying the globe is warming up, we're really worried about something bad might happen. We can't tell you what, we can't tell you how bad it's going to be or when it's going to be, but we're worried. And then on the opposite side, in the climate case, you've got experts in the energy system worried about the costs and the impacts of making an energy transition. And so you got to balance the two sides, and we have not been very good at having that balancing conversation.
You know, implied, I find, in the COVID debate and the climate debate is a question about the status and role and place of science in society. And in the philosophy of science, there's a distinction between the scientific and the scientistic. So science is a guide to the facts, a tool for use in the service of our values, and science is a guide to what our values should be. And that's scientism, you know, rather than science. And I find that there's a general tendency for people to see scientists in lab coats as kind of the new priesthood, who are somehow above the fray and they can inform us not just on the facts but our values. And I wonder if you could talk about the problem of scientism as expressed in the climate debate. Do you think there is a scientistic problem in?
Oh, yes, absolutely. And, you know, in my experience, and I've done a lot of informing of decision makers, whether in the government or in the private sector, about technical matters, I think the role of the scientist is to lay out the facts, the pluses and minuses of certain courses of action, as well as we can project them, and then let the decision makers add in those values and do that balance. And climate science is particularly infected or afflicted with scientists who've crossed over that line and say, I know what the world needs to do, and I'm going to spin the science to make that happen. It's particularly pernicious, I think, because, as my wife will tell you, scientists are particularly bad at values judgments. And I think when we blur those, we have done a scientific malpractice. And you know, you can find Phil Handler, who was president of the US Academy of Sciences in the late 70s, I think. He's got a wonderful editorial in Science magazine about exactly that topic and warning scientists don't cross the line. Of course, Phil is long gone, and it is endemic in climate science.
I mean, this is kind of a broader point maybe about academia, but I remember, I not so much remember myself, but I certainly am aware that in the late 20th century, there was an increasing awareness that science doesn't have all the answers, that it's a useful tool that needs to be managed cautiously. Philosophy of science was concerned about issues like scientism, scientific method, and so on. And I do feel there's been this suddenly we're all enthralled to science. I find that science had a comeback and we've lost the lessons of humility about it from the late 20th century. If you think that's true, and I don't know if you do, why? What's changed?
You know, we have seen in the last, several decades, spectacular progress in science, but more in technology, that touches people's lives in wonderful ways. We're seeing more and more. Fusion is making great progress. We're currently debating artificial intelligence and how it should be applied and so on. And so I think we're seeing more of it in part because the pace of advance is more and more. And again, you know, I'd like to be the referee, and let's keep the debate clean. Let's understand what the science says and then understand how the values come into a decision. But a lot of society just wants to jump right to the answer.
Well, obviously, yeah, I'd agree that culture in general, people have become to, well, we've seen the great successes of science recently, particularly in computing and so on. And so there's this great, not just respect, but increasing deference to science. What do you think the public should know that they don't know about science to bring everyone back to a slightly more, I suppose, more judicious view of it?
Yeah, I think...
as a computational scientist yourself.
Yeah, first of all, there are several things. One is, of course, computer modeling is not the be-all and end-all. As George Bach said, all models are useful and most are wrong, or something like that. Sorry, it was all models are wrong, but some are useful. And the precision with which the lay public gets quoted climate stories is appalling. All right. So first thing is nobody's certain about any of these things. I think the second is if you hear a scientist saying the world has got to decarbonize, that scientist has probably already made up their mind and is giving you an opinion rather than a scientific fact, because there are countervailing considerations to a rapid, large-scale decarbonization of the world. So try to separate fact from opinion. Be skeptical of projections. And I think the third is when you hear it's unprecedented storm or fire or whatever, or the worst since 1970, you know, the thing I teach my students is ask what happened before 1970. And, you know, extreme weather is nothing new. And as I said, most extreme weather phenomena show no long-term trends.
So I just asked you about what should we all consider to bring us to a more accurate view of science's role and place in nature. But I suppose it's kind of the accompanying question to that is that what do you think we're misunderstanding about ourselves, about society, when we talk about being guided in our action by computer modeling?
Society is real complicated, and you know, as a 50 years ago, I would have not have said that as a physicist. But as you grow older, you realize the real problems are societal problems, and they're real complicated. You know, there's a famous H.L. Mencken quote, there's a neat solution to every human problem, neat, simple, and wrong. And I think we need to understand these are multi-dimensional issues. There are no silver bullets, and we don't tease it all apart, in part because I think our own perspectives are usually limited. We live in pretty prosperous countries, reliable energy, adequate food, law and order, and all that. Most of the world does not live like that. And if you're going to make decisions about global issues, I think you have to hear the perspective of the 6 billion people who don't have enough energy, for example.
Do you think it's possible to separate out a discussion of climate change from politics? Or do you think there's always a political agenda involved in whatever the perspective is? You know, do you think is it a topic we can talk about?
I think about the science you can have in the end in a political discussion. I take the IPCC Working Group 1 reports as gospel. They actually do a pretty good job when you read the 3,000 pages of the report. When you read the summary of the report for policymakers, it's terribly distorted. But they leave out things, and I can give examples. But the scientists, when you talk to them, everybody will agree. When I wrote the book and I talked to some people in the community, they say, Steve, you got it just about right. But I can't say that in public.
That's interesting.
Yeah.
Well, this actually brings us to an interesting question about what sort of reaction did your book provoke, and can you just give us a sense of the general reaction?
Yeah. So we've sold about 200,000 copies, translations in about a dozen languages. And needless to say, when I finished up the book, I was pretty nervous about how it would get received. Wasn't too concerned about it, but I was nervous. I was much more concerned about making some terrible mistake in the science. Yeah. And so, of course, I had a number of friends who read drafts, who were deeply knowledgeable about various aspects and made appropriate corrections. I've been most gratified by the many emails I've gotten that have said, thanks for providing a framework for how to think about all of this, and for providing references where I can dig deeper. On the other side, I've been appalled at the behavior of some of my senior colleagues, scientists, most of whom I don't know personally, who would write reviews that basically are filled with ad hominems that put words in my mouth. Some of them admitted that they hadn't read the book, but wrote the review anyway, and just completely got it wrong. And I'm more than happy to engage in a serious discussion, but this was just basically some of the reviews they're silly when you read them. All right.
Why do you find the climate debate, and I've encountered this as well, the climate debate, why do you think it provokes such strong emotions? Because I can't think of any other area of science that provokes people personally, politically, emotionally, in quite the same way. And I don't think it's simply down to the significance of it. I mean, perhaps you could look at the nuclear debate in the 1970s and see it as provoking politics. But is it simply because it's seen by certain people as a cataclysm of some sort? Or is there something else going on?
Well, the more paranoid folks on the skeptical side think it's a vehicle toward greater government control of our lives. And certainly if we were to decarbonize rapidly in a large way, it would mean greater government intervention. And so there is that, if you like, consequence of it. I think also it's a complicated subject, the climate side, and it's easy to make unsupported arguments. So, for example, I saw today in the paper, somebody says, wind and solar are the cheapest ways of generating electricity. And that's in fact true at the moment, but that's not the end of the story, because wind and solar are extraordinarily unreliable. And if you want the kind of reliable electrical system that we've come to expect in the developed world, you can't build it on wind and solar alone.
Yeah. So, do you think you can look at the science of climate change and derive from that any guide to action?
Boy, that's hard. Yeah, I think so. You can look at, for example, how rising temperatures have affected the human condition. You can look at how volcanic eruptions, which put aerosols in the stratosphere, how much they've cooled the planet, and get some sense of the efficacy of geoengineering schemes or the sensitivity of the climate system. You can look at the way in which the carbon cycle works and varies and get some sense of what sequestration might do for you. So there are vague clues, but the real questions about what you might do about this are cost, efficacy, and scale. And unfortunately, those are really hard barriers to overcome.
How do you mean cost, efficacy, and scale? You mean in terms of what would be required to do something?
Yes.
And they're just simply they're too large?
Yeah, so the cost, at $100 a ton, you're talking $500 billion, if I've done the math right, to remove carbon dioxide. That's at $100 a ton, or price carbon dioxide. Let me see if I got that right. Yeah, I think that's right.
But that's really a question of trade-offs, right?
Absolutely.
And so it's, in the context of that, obviously we talked about COVID before. I mean, my perception of COVID was that there was quite a sort of slightly monomaniacal focus on a single variable, when of course our lives are affected by many sources of risk and many challenges. And I do feel, certainly in the British context, there wasn't sufficient debate, and this is not to make a position on what the answer should have been, but there wasn't sufficient debate of what a balanced approach would be, because everyone was singularly focused on the COVID issue. And I'm wondering, are there any lessons from how COVID was handled, and some would say even mishandled, for how we think about climate?
Yeah, you know, for better or worse, at the beginning, let's say the first 6 months of the COVID, let's say the first half of 2020, it really was an emergency. I mean, people were dying, and at unsettling rates. And I think the government felt it had to do something, and it did. Not only the lockdowns, but also the vaccine development, which is a wonderful piece of science. Climate's different. There is no climate emergency, okay? Climate plays out over decades. We've got time to understand this better and to think through the responses, both the technology development and the rate and extent to which we want to deploy. So it's a little bit different in that sense.
I'm curious, actually, as you mentioned that, there's a lot of how we think about most issues involves us using a lot of analogies, a lot of metaphors, and often there's a lot of these types of metaphors we use that I feel go unexamined. And one I often think about with climate is the concept of a tipping point, that we get through a certain 1.5 degrees and there's a tipping point. Do you think these sorts of metaphors are helpful? Are they science accurate, or are they marketing, in a sense, for the theme?
Well, first of all, if you believe in tipping points, and we can talk that for a second, there's a wonderful paper in PNAS in 2021 where they have examined the economic impact projected of 8 different tipping points, including the slowing down of the Atlantic circulation, outgassing of the permafrost, dying of the Amazon, and so on. And they add about another percent to the few percent associated with the warming itself. And even when the tipping points occur in combination. So at least some of the official science says, even if it happened, not so bad. Now, whether it happened or not, the models show nothing like this at all. The historical record, well, we had the Younger Dryas, for example, which you may know was a sudden cooling about 12,000 years ago. I'm not worried, and I think the IPCC downplays this.
The IPCC, what, sorry?
Downplays
it.
And, you know, again, I come back to values for a minute. You really need to be thinking about this from the perspective not of the billion of us, 1.5 billion, who are sitting fat and happy. You got to talk about the 6 billion people who don't have enough energy. And you ask them, are you worried about tipping points? And of course they'll tell you, absolutely not. I'm worried about how I'm going to keep my fridge running, or how I'm going to get light to study at night, rather than some vague, distant thing that's going to happen way in the future.
So the concept of climate change as a concern, it strikes me that it's quite an interesting, its origins are worth talking about, that it seems to have come out of not just the global north, but in my understanding and my observation, the formerly Protestant countries. I think Max Weber said the greatest legacy of Protestantism was secularism, and secularism seems to keep bringing us new priests in this case, white coats. And I wonder, do you think there's a kind of a cultural way of looking at the preoccupation with climate? Because as you say, if you go to many parts of the world, it may not be the first concern people have in the context of the risks they face. So do you think there's a cultural element, or is it purely a scientific
no, it's certainly cultural. And I like to quote, there's this social scientist, Anthony Downs, who in 1972 wrote a paper called Up and Down with Ecology. It's a wonderful paper, about 30 pages long. And one of the great quotes he's got in there is that he was watching the smog get worse and worse in Los Angeles as more and more people got cars. And he says the elite's environmental deterioration is often the common man trying to improve his lot. Right? So think about that for a second.
Repeat that sentence again.
The elite's environmental deterioration is often the common man trying to improve his lot.
Oh, interesting.
All right.
Okay, so that's interesting because what you've said could imply a kind of political agenda to keep the people down, sort of thing.
Yes,
Yeah.
right.
And do you think
Carbon
that-
colonialism, it's
Yeah.
been called climate colonialism.
Yeah.
And you hear that if you listen to Modi from India talk
Yeah.
or people from sub-Saharan Africa.
Yeah.
They're basically saying, you got yours, you cannot and should not prevent me from getting mine.
Now, is that an implication of the climate narrative, or do you think it's an intention?
I don't know. There's so many people involved, it's hard
Yeah.
to say. But I think
Well, that's fair, so we can't generalize.
it's structural to the global north-south inequality. And so, just to come back on that for a second, I mean, when the World Bank says we're not going to fund a coal plant in Vietnam because of the carbon pollution, I would say that's immoral, because those folks need the energy. And who are we to tell them not to do that?
Interesting. So, in terms of the implications of your book around what, if anything, needs to be done, so obviously you have a critique of the science in it. I think you point to questions that we're not addressing and should address. So there's the questions we are addressing and the problems. There's the questions we should be addressing, perhaps aren't. But what sort of policy recommendations would Professor Koonin make around climate?
So I mean, there is a second edition that will come out in mid-June, and there was a section in there of what would I do if I were in charge, right? And so the first thing is, let's keep the science going. It's very important that we have continuous, precise observations. So do not stop the observations. Keep them better. We need to work harder on the oceans, which is really where climate happens, and we have terrible knowledge of the oceans. I think the second thing is stop running so many damn climate models. The IPCC spends an enormous amount of computer time and running different scenarios. You don't really learn anything new from that. A little more thinking and less computing would be a good idea. I think we also have to acknowledge that the present and foreseeable generations of climate models do a terrible job at the regional and local prediction level. You can't tell whether with a warming you're going to get more rain or less rain. And you can see that in the IPCC reports, and the experts will even say that in private.
Sorry, go ahead.
No, so that's on the science bit, all right? I think then on the response, we need to acknowledge that there is perhaps a long-term problem, but there is no emergency. We have time to think it through. I think we also need to acknowledge the legitimate energy needs of 3/4 of the planet's people, and we need to make sure that those are satisfied. On the energy technology side, there are no regrets deployments of things, certainly efficiencies to the extent that they're cost effective. Nuclear energy, I think, is going to be a big part of the solution. And then there are technologies to develop. Low emission chemical fuels, better grid management, grid scale storage to the extent that we can push that, carbon capture and storage, all worth researching, but I would hold off crash deployment of them because they're going to be disruptive and increase the costs. And I would make sure that we not go too fast. I think we're already starting to see, particularly in Europe, a political pushback of the attempt to go too fast. And we're going to see it soon in the States as well. And that will be terribly counterproductive to the economy and to any attempt to significantly reduce emissions.
That's sort of the road to hell is paved with good intentions.
Absolutely.
So you talked about modeling before and the problems with modeling, and of course your background as a computational scientist. Could you just, in layman's terms, talk about the problem with modeling, or really what is modeling trying to achieve, what are its limits in general?
Yeah, so what we would like to understand is how will the global and local climates change as human influences grow? Not only greenhouse gases, but aerosols as well. In order to do that, you build this big computer model, which basically consists of tens of millions, or maybe 100 million voxels, squares, stacked up into the ocean, down into the ocean and up into the atmosphere. Typical square size these days is about 100 kilometers on a side. And then what you do is you use the basic laws of physics, conservation of energy, momentum, matter, and so on, to trace the atmosphere and the energy, sunlight, infrared radiation, through these boxes 10 minutes at a time. Okay. And then you run that for a couple centuries, 10-minute time steps, make sure the climate looks about all right, and then turn on the greenhouse gases. Right? And to the extent that the temperature goes up, you say, I figured out what the sensitivity is. All of that sounds fine in practice, fine in principle, but in practice, it's really tough. All right? Let me just give you a couple of reasons why it's hard. One is that the boxes, as I said, are about 100 kilometers on a side. Weather phenomena, think thunderheads or clouds, happen on much smaller scales. You can't describe that explicitly in the computer, and so you have to make assumptions. If the temperature in the box, which is only one number, is such and such, and the humidity is such and such, where are the clouds? What kind of clouds are they? Nothing tells you how to do that, but you have to look at observational data, general physical principles, to make what are called these subgrid parameterizations. Different people make different subgrid parameterizations, and so you get different answers from different models. There are about 50 different models the world uses. They give different answers, and the numbers you see are the average of models that disagree with each other and often disagree with the observations. So subgrids is one problem. You might say just make the grid smaller. The problem is that the computational effort goes up as the cube of the grid size, right? So if you made it not 100 kilometers, but 10 kilometers, it turns out you need 1,000, roughly 1,000 times. Does that get that right?
So you need exponentially more data.
You want more computational power.
Yeah.
So let's talk about the data for a minute. All of these models, you got to start off somewhere. You got to say in 1950, the state of the atmosphere was such and such, and the currents in the ocean, and the temperature and so on and such. We don't know that at all. And so people make assumptions about what that is. That's why you get such a range of predictions or range of results in these models.
Yeah. I mean, do you think there's such thing as a model that if we just had, people often say if we just had enough data, in other words, give us more funding and more computing power, we'd eventually arrive at a more accurate model. But do you think there are intrinsic limits to what modeling can achieve?
Yeah, I mean, first of all, the system is chaotic. And so you run the same calculation, but change one digit in the starting conditions. You get completely different answers in detail. The hope, though, is that the gross properties are predictable. And I like to use the following analogy. Consider a pot of water that's being heated and is boiling from the bottom. You can't describe in detail all of those bubbles roiling, the motion of the surface, and so on. You just don't have enough computer power to do that. But you can describe, quite simply, the rate at which the level of the water goes down and boils off. So the hope is that the gross properties of the system are predictable, never mind the details.
I suppose this leads to an interesting question and problem around policymaking, because climate modeling, I think, is intrinsically general. It's 30-year rolling average. It's a global model. But obviously, policymaking always has to be specific to a time and place, this nation now. And are we talking about, sometimes I wonder if these are simply different frames of reference, that they exist in different planes of understanding the world. In a sense, the planet has always been there, but a planetary frame of reference has not. So we talk about climate a lot. It's a very interesting topic for people, I think, because it has a sense of totality to it. But a given policymaking is always localized. What value is it?
Yeah, localized not only in space, but also in time. The political horizon is a couple of years at best, right? And the people who build and operate the energy system have managed to ride through that political cycle. Energy systems take decades to change because the equipment lasts a long time, they need to be highly reliable, and there's big capital investment involved. And so the political system has not had as much influence on the energy system as it would have liked for those fundamental reasons. I've often thought, with a US perspective, what's the longest institution that we've been able to keep going, or the longest technical innovation? And I came up with the interstate highway system, which has been in existence for probably...
It's Robert Moses.
Well, no, Dwight Eisenhower.
Yeah.
Okay, so from the 50s. Yeah. Social Security maybe is 100 years, roughly. Yeah. So you need those kind of longevity in the thinking, and we just don't have it.
One other question, and then we can open it up to questions, I think. And I forgot to bring the Slido on stage, so if people don't mind, if they've got any questions, asking verbally. But you mentioned oceans and the importance of oceans in modeling climate. Can you just talk briefly about why oceans? What's the difference?
So when heat gets added to the planet, which it is, the planet is acquiring heat, 90% of that heat winds up in the ocean because the ocean has a much greater, technically, heat capacity. It can absorb a lot of heat without changing its temperature too much. And so we see the oceans warming, but not to be alarmed because it's at the rate of about a 1/20th of a degree per decade. It's not very much at all. And when you look at the historical and geological record, to the extent we've had it, it's been warming since 1650, the depths of the Little Ice Age, warming more rapidly now. Whether that's greenhouse gases or the sun or something else remains to be determined. But understanding the oceans also have a long time scale. The atmosphere changes on a 1-week time scale, right? That's weather prediction. Whereas the oceans, the mixed layer, the top layer, top 50, 100 meters of the ocean, has about a 10-year time scale. And there are currents, massive currents in the ocean that transport heat around that have a 1,000-year time scale. So they change on the, so you got to understand those also if you're going to be able to predict climate on that time scale. And we don't.
I've lost more questions, but I thought I should just open it up. Yeah. I'm sure there's questions in the audience. Anyone got any questions? At the back there. One second, let me just bring the microphone.
The constancy of the sun. How much data? What can you tell us about the source of energy? How constant it is over what scale, and particularly in the domain of spectrum, which actually matters.
So let me. You know a lot more, I know, than your question implies. But let me, for the rest of the folks. The energy from the sun is what drives the climate system. The intensity of the sun, how much energy it delivers per second, is a primary determinant of the temperature, for example. And so we do our best to measure it. One way of measuring it is through satellites. We have radiometers that measure the intensity. And if you look at the total energy coming out from the sun, over the last 50 years, yes, it shows small fluctuations with the sunspot cycle, but those fluctuations are much too small to account for the temperature changes we see. If we go back using various proxies, beryllium measured, we can go back thousands of years. And again, pretty small variations are inferred. What Professor Rafalski is referring to is it's not only the total energy that's coming from the sun, which is mostly sunlight, but the ultraviolet light which is coming out of the sun, cosmic rays, and so on, which may have secondary impacts, for example, creating more clouds or not in the upper atmosphere, that might influence the climate. The IPCC's contention is that all of that is too small to matter, at least on the time scale of the many decades we're concerned with. There are people who credibly say, hey, I found a solar signature in the climate data, but not widely accepted yet. So unsettled, shall we say.
Thank you. Any other questions? There was another hand up before, I think. Oh, there we go.
Nobody going to disagree with anything?
The heat content of oceans in the past years increased by 100 zettajoule. In the same period, the energy use of the humankind is around 10 zetajoules. Since from the Industrial Revolution, it has been used only 40 zetajoules. So for the why it is not a clear proof that the mainstream idea is incorrect?
I suppose, sorry, implied in that is this question of whether we, do you find when we talk about climate, we have perspective? I suppose the question is about perspective of there are many things going on in the world, but when we fixate on one topic, is it a fair analysis?
No, I think there are, if you ask what's going to get us, as Bjorn Lomborg does, for example, I think climate comes out number 9 or 10 on the list. I think there are many other, both natural and human-caused phenomena that we need to be paying a lot of attention to. Climate has been unreasonably elevated. That's a value judgment on my part. So again, I'm a scientist. I don't have expertise in this. But if you look at the risk, which is the hazard times the impact, it doesn't come up real high on the agenda. With respect to other sources of heat, both geothermal and anthropogenic, human-caused, I think the geothermal is about 1/10 of the anthropogenic radiative forcing, so 0.25, 0.2, and the human energy use is an order of magnitude less than that. So human energy, apart from local effects like urban heat islands and temperature stations near airports and so on, globally average, it doesn't matter at all. Geothermal, also not so much, but there are localized geothermal effects that I think are unsettled, particularly geothermal under the ice sheets in the Antarctic and Greenland that can be lubricating the sheets and making them flow more easily than they would otherwise. Unsettled yet. I mean, the general problem is human influences, 2.5 watts, are small, and so you've got to consider a broad range of phenomena that are comparable in strength. And you better be sure you got them all before you say, aha, that's CO2.
So when you look at the threats facing humanity, people, you say you don't like the term climate emergency. So what are the emergencies, if any?
I don't know about emergencies, but things that can get us.
Yeah, what would you see as the priorities?
Coronal mass ejection. If the sun emits in the right direction or the right amount of particles, it will do a lot of damage, bring society to its knees by knocking out the grid. Fortunately, we watch that and try to put measures in place. There's the proverbial asteroid, of course. A large volcanic eruption. We saw Tambora wipe out agricultural production for a couple summers, right? The year without a summer,
I also remember the Iceland volcano in 2009. It was actually quite disruptive to the current economic system. It was disruptive.
But over 2 seasons or something, which is about as how long the aerosols would last, to cut down the sunlight and thereby cut down crop production, that's pretty scary. All right. The pandemics, of course, as people live closer to nature and travel more and live closer to one another. Don't have to mention that anymore at all. And then things we do to ourselves.
Yeah.
Right.
Any other questions, please?
Steve, you forgot a very important killer, GRB, gamma ray burst.
Yes. Okay.
Which every 2.5 million years fries half of our planet.
Yeah. Thank you. I mean, the universe more generally is a much more violent place than we think. Just because our own time span is.
Well, this actually brings to an interesting point I actually wanted to bring up, which is that my sense is, there's a whole area of academic research called disaster risk reduction scholarship. And they have like a central sentence that they've been dining out on for 40 years, where they say, earthquakes don't kill people. What kills people is collapsing buildings. And the point is that the natural hazard isn't really the disaster is always social. And I think sometimes we always forget in society that the world is trying to eat us. If you didn't have the culture we have, the built environment, the clothing and so on, most of us would be dead in 72 hours from exposure. But we are surviving not because the world is a safe place for us, but because we have collectively come up with effective ways of problem solving.
Yeah.
And I wonder, therefore, when we think about these issues like climate or indeed any other issue, whether the problem is really the climate first and foremost at all, or whether we are really talking about social problems. It's about how, because we have this phrase now, climate adaptation, but there used to be, in my sense, an old word for adaptation, which was simply culture. There's a reason why the Swiss have different roofs to their houses than the Croatians. Right. So what do you think of that, this idea that the real problems are social?
I think that we can create resilient societies. We have been doing that. So the death rate from extreme weather has fallen by a factor of 50 over the last century. Many fewer people proportionally die. And the reason is that we've gotten better at predicting storms, floods, and building structures that will mitigate those risks. I think if you ask me, what is the dominant way that society will respond to a changing climate, it's through adaptation. And a cardinal rule is we should at least adapt to the past, and we don't do that. I mean, you get disasters like Katrina, others where you knew it happened before, and there were people who warned you it was going to happen again, but society didn't do anything about it.
There's an interesting paper written in 1995 by Anthony Oliver Smith about Peru's earthquake of 1970, and he described it as Peru's 500-year earthquake. And his point was that the Andean peoples had been exposed to earthquakes for 10,000 years, but it was only with the Spanish arrival 500 years ago that they started to build in a way that wasn't adapted to earthquakes, started to build cities in the earthquake epicenter, and all these sorts of things. And it
they
suggested,
didn't know about it.
Yeah, right, and it's or indeed they did, but they didn't care because they had their own Spanish traditions of building and so on that they wanted to do. So it's interesting because it highlights the social aspect.
So there are two different ways of earthquake adaptation, right? The Western way is we build the buildings resilient and flexible and so on. The Japanese way is you build them light and cheap and then expect to rebuild when the earthquake happens, right? So,
I thought there's probably a third way, which is don't build on the epicenter.
Well, there's that too, but who knows exactly where the epicenter is going to be, right?
Yeah.
San Andreas will break anywhere along the fault.
Not true. Any other questions? No? Well, we're running near the end here, so have you got any final thoughts around the book? Why should people pick up the book? What's your pitch for the book here?
I tried to portray in non-expert terms the real situation on science, on climate science and energy. The words are not right, but the ideas and the references right out of the official reports. And so if you want to get a way of thinking about these problems and some sense of what they really are or aren't, people say the book is a good read. The best introduction I've had in the last couple of years was from Benny Pizer, who is the executive for the Global Warming Policy Foundation. And he said, he compared me to William Tyndall. For those of you who don't know history, and I confess I didn't, I'm educated as a scientist, not with a liberal education. Tyndall was a major figure of the Reformation, and in the early 16th century was the first to translate the Bible from Greek and Hebrew into English. And that, of course, allowed everybody to see exactly what was in the Bible, and it did not agree with what the church was telling people. Of course, Tyndall was later burned at the stake for that heresy, among others. But this tries to just tell people, what does the science really say? And it's different than what you've been hearing from the politicians.
To be burned at the stake, we need to translate it, though. It means carbon emissions.
Oh, yes, there is that too.
Carbon emissions. Well, I'd just like to, I think we should all thank Professor Koonin very much. Thank you very much for the talk. Thank you for coming out to Budapest.
Great.
And
Okay.
It's been a real pleasure. Thank you.
Okay,
Thank
thank
you.
you.